Okay, welcome back. Apologies for the long delay. There was a major change of tack with the third microcode called PleX. Now I had intended to finish the edge panels and connect the centronic socket for the system printer and MIDI sockets for some musical fun, but this meant taking the machine apart, and I didn't want to rock the boat before PleX was fully working. So now it is working. Before PlasMa goes in for surgery, this video is all about PleX and how it differs from those used in previous videos. And I'll finish off with some examples loaded from paper tape. A toy instruction set was designed purely as a teaching aid, whereas PleX is more advanced to take full advantage of PlasMa's features and peripherals such as mag tapes and discs. In my earlier homemade attempt at designing PleX was a failure. I'd used similar tricks to Toy B, which gains more opcodes by restricting some of them to the first 8 registers only. For example, the load register with address function is limited to registers 0 to 7. And this was quite restrictive, and as more and more functions were added, the whole thing became too unwieldy and difficult to use. So I ended up throwing the towel in and looking for an existing design, which is when I came across a really neat instruction set called Nice by Bernd Ullmann. Hope I pronounced that right. The links are here and in the description below. And they're worth looking at if you're interested in old computer systems, including analog computers. And Nice was originally for a 32-bit machine, but Bernd also designed a cut-down 16-bit version called QNice, where the Q appropriately stands for quite. Now it uses 16 16-bit registers, so it's a good candidate for PlasMa as the 16 rows of lights were already in place. There's no point emulating an instruction set which only uses a couple of registers, such as the 6502. It's all about the lights and switches after all. That's what the L, A and S stand for in PlasMa. And there was no need to be compatible, unlike the toy emulations, so I've cherry-picked lots of ideas from QNice and adapted them to fit the PlasMa hardware. The changes include replacing interrupts and register stacks with instructions for the 32-bit accumulator and some which are more memory efficient. So I'll run through some of the main features and contrast them with toy where relevant. The main group of instructions operates on 2 operands, a source and a destination. And as with toy, 4 bits are used to access up to 16 registers. So that's 4 bits for the opcode, 4 for the source and 4 for the destination. So this instruction 1304 stores the contents of register 1 into register 3. Here's the function 001 for the move, 0011 for register 3, 0001 for register 1. Now I've used the same convention as the toy emulations, where the destination operand always comes before the source. I'll preload register 1 with a value 5678. Press step, and the value is now in register 3. Here's the converse instruction, which loads register 1 with the contents of register 3. I'll clear register 1 and press step. And there we are. Now you may have noticed the same opcode is used for both load and store, which saves having to define 2 separate opcodes as with toy. Now this is a good thing. If you've ever tried designing your own instruction set, you'll find the number of opcodes is one of the many compromises to consider. You run out of bits very quickly. And the other opcodes in this group include the usual ones such as add, subtract, shift and so on. But up to now this seems to offer less functionality than toy, which had 3 operands, 2 source and 1 destination. So where's the gain? Well, it's those 4 spare bits. 2 bits are allocated to each of the 2 operands, and they represent address modes. This means there are 4 possible address modes for each operand. The 00 is direct, which means the contents of the register. 01 is indirect, which means the contents of memory addressed by the contents of the register. 10 is indirect post increment, which is the same as indirect, except that the register is incremented after being used. And finally, 11 is indirect pre-decrement, which is the same as indirect, except that the register is decremented before being used. Right, and here's an instruction which uses the post-increment mode. I'll load memory address 100 with 1234. I'll load register 3 with that address, 100. Now if I press step, the value 1234 goes into register 1. And register 3 is automatically incremented to 101. So if I was processing an array, say, I could just loop back and repeat. Now this may not seem much, it just saves a separate instruction to increment register 3, but when you don't have much memory to start with, it all adds up. And this is just one example. Now what about literal or constant values? Well, toy has a load address instruction which can load 8 bits into a register. Now, this is okay for addresses, but PleX has more memory than toy, so it would be nice to load a 16-bit value. But there are no spare bits in the instruction, so how can it be done? Well, the answer uses an idea from QNice, modified for PleX. One of the work registers is sacrificed, register 15, or RF, so that number, 15, can be used to indicate a literal. Here's the instruction format for a literal to be used as a source. The 4-bit source field is the value 15, or hex F. The instruction also needs to know where to find the literal, and there are no bits left to hold an address for it, so the second trick is to store the literal immediately after the instruction. This means the whole instruction occupies 2 words of memory, but the payoff is that you can load or operate on any register with a full 16-bit literal. If you're familiar with QNice, you'll know that it uses the program counter PC as register 15 and uses the post increment mode to access the literal. But this can cause all sorts of control flow problems, so I've decided to simplify it for PleX. Now I may have misunderstood some of the advantages with the QNice system, but we'll see how it goes. Now the row of lights on the front panel representing register 15, or RF, for toy, are now reused in PleX to display the literal value. And the row can be considered an extension to the instruction register, IR, so it's renamed as IR2. And it always shows the contents of PC plus 1, as opposed to IR, which always shows the contents of PC. And a nice bonus is that the load and breakpoint system can still be used on this value. So here's an example which loads register D with the literal 1234. You can see the instruction in IR and the literal in IR2. If we press step, register D is loaded. Now the next group of instructions are for jumps and calls, and these can be unconditional or conditional depending on the state of the 5 flags. There's overflow, negative, 0, carry, and all ones. Now there are no flags in toy, so its conditional jumps can only test the state of register contents. The PleX system is more versatile, as the flags are set depending on the destination contents, which could be a register or a store location. The flags are also set by other instructions, such as compare and IO calls. The jump and calls both use a single operand to specify the target address, and this can be absolute or relative, and the operand has the same address modes as before, so they can be direct, indirect, literals, and so on. The condition bits refer to the flags to be tested. The invert bit inverts the condition logic, so you can, for example, jump if carry or jump if not carry. The two type bits give 4 combinations, which are jump absolute, jump relative, call absolute, and call relative. The source is, as before, a register 0 to 14 or a literal indicator, and the mode is the address mode for the source. The call instruction is for use with subroutines. A toy has a subroutine mechanism using the jump and link instruction, which uses a register to hold the return address. The subroutine jumps to that register's contents in order to return. The problem with this is that you need to preserve the register somewhere if you want to use nested subroutines. And you also need to agree on a convention across all your subroutines as to which registers to use. Now the call instruction in PleX avoids these problems by using a stack to hold the return address. The stack lives in main store and is addressed by the stack pointer register SP. And the convention is that SP is incremented before storing the value. This means the stack grows downwards, so can be placed at the top of store, and SP always points to the last item pushed onto the stack. The call instruction is the only dedicated stack-based instruction, which begs the questions: how do you pop the return address, and how do you push and pop other values without using special instructions? Well, the answer is another trick from QNice, where one of the work registers is used as the stack pointer register, so it can be accessed using normal instructions. PleX uses register 14 for this. Now this may seem a waste of yet another work register. We've already lost register 15 to allow literal access, but the pros outweigh the cons. There are no further restrictions on any of the other 14 registers, and you can still use register 14 for general purpose as long as you don't use the call instruction. So how do you return from a subroutine? Well, you just jump to SP, which is register 14, using the indirect post-increment address mode. This jumps to the item on the stack, which is pointed to by SP, the return address, and then increments SP, so it points to the previous item on the stack. And what about pushing and popping other values? Well, pushing uses the pre-decrement mode with SP, so it's decremented first, then the item is stored at that memory location. The popping does the reverse. It's the same as the return example. It retrieves the item before incrementing the stack pointer. Right, next up is a group of instructions which allow small embedded literals. As we've seen, the general instruction group expects 16-bit literals to occupy the word following the instruction, but this can be quite wasteful of memory, especially if the value is very small. The short literal instructions allow small values to be embedded within the instruction word. Here's an example which loads the value 7 into register 1. Only one instruction word is required. There are a couple of trade-offs. Only one bit is available for the address mode, so only 2 address modes are possible, direct and indirect. And the value is limited to 4 bits, so can only be 0 to 15. Now, a similar scheme is used for jumps and calls, which allow small relative offsets. Right, finally, there's a miscellaneous group which includes some accumulator functions and also a system call. And the system call is a way of expanding the instruction set without using any more opcodes. It has a single operand, which can be a register with the usual 4 address modes, or a literal, and the target 16-bit value is treated as a function word, similar to toy B, but offering many more functions. These include I/O controls for all the peripherals, more accumulator-based functions, and more arithmetic functions such as multiply and divide. Okay, that's enough ones and noughts. Let's see some programs. Now I've converted the old bootstrap routine into PleX code and luckily it still fits into the 16 words of fixed store. So that's now being loaded, so the machine is ready to load from paper tape after switch on once the microcode is loaded. It's now waiting for a paper tape to be loaded, and this one contains the PleX version of NIM. And this tape holds the PleX version of the 16-bit calculator. I've used a more informative title with this version, as PleX has more store than toy. And the calculator can only handle values up to the limit of 16-bit registers, which is roughly plus or minus 32,000, although it could handle larger values with more ingenious programming to make use of the carry and overflow flags. Now that's outside my skill level, but I've made a version to demonstrate the 32-bit accumulator, which gives a much larger range for free. This one can handle approximately plus or minus 2,000 million. And I can now use it for my favourite calculator party trick. Enter the values 1, 2, 3, 4, 5 up to 9. Pick your favourite digit. Did you say 3? OK, multiply by 27, and there we are. Enter the values again, 1, 2, 3, 4, 5 up to 9. Pick another favourite. Did you say 7? OK, multiply by 63. Magic. Finally, here's my first attempts at a simple control program, or mini exec. It's very early days at the moment. It just polls the peripheral states every few seconds. So you can see the paper tape reader is still on from the previous load. If I unload it, it changes to off. I'll load a mag tape. There's also a command prompt which toggles on and off, and it currently supports just one command for setting a time of day clock. Right, that's it for now. See you next time, hopefully with a fully sealed case.